Hello there and welcome to Theories Before Sleep. I'm so glad you're here. Maybe it's been a long day, your thoughts still circling through endless tasks. Perhaps your mind is restless, seeking something to quiet the noise. Or maybe you're simply curious about cosmic creation, drawn to the mystery of how everything began, searching for something peaceful to carry you into sleep. Tonight's journey is for you. You don't need to do anything but rest. Let your breath slow, your thoughts soften, and your body grow light. There's nothing to memorize, nothing to solve, just gentle wondering. We're going to explore 100 theories about cosmic creation, not in a rush, but slowly, gently. From the first spark of existence to the endless cycles of universes being born and dying, each theory a quiet doorway into wonder. Some will feel familiar, others strange and distant. All are presented to help you drift peacefully towards sleep, one soft mystery at a time. If these explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now let's begin. The first theory is waiting, patient and quiet. The universe began from absolute nothing. Some theories suggest the universe emerged from complete nothingness, not even empty space, but the absence of existence itself. This idea addresses perhaps the deepest question humans can ask. Why is there something rather than nothing at all? Physicists have explored how quantum mechanics might allow reality to spontaneously appear from a state of pure void, where even the laws of physics didn't yet exist. In this view, nothing is unstable. The universe didn't need a cause or a trigger, just the strange quantum possibility that nothingness could fluctuate into somethingness, the way virtual particles briefly appear and disappear in empty space today. Our entire cosmos, with its galaxies and stars and planets, might be the ultimate quantum fluctuation, a temporary ripple in an ocean of void. The theory remains speculative, dancing at the edge of what physics can describe, yet it offers a strange answer to an ancient question, suggesting that existence itself requires no explanation beyond the mathematics of quantum uncertainty. No creator, no prime mover, just the restless nature of nothing becoming something. The Big Bang was not an explosion in space. The Big Bang wasn't an explosion that happened somewhere in space, but rather the expansion of space itself from an infinitely small point. This distinction confuses many people, because we naturally imagine explosions as events occurring within a container, matter flying outward into emptiness. But the Big Bang had no container, no surrounding void to expand into. Space itself was born in that moment, carrying matter and energy along as it stretched. Imagine the surface of a balloon being inflated, with galaxies drawn on it like dots. As the balloon expands, the dots move apart, not because they're travelling across the surface, but because the surface itself is growing. Our universe works the same way, expanding in dimensions we cannot visualize, pulling galaxies apart not through their motion but through the growth of space between them. This theory, supported by decades of observation, fundamentally changes how we understand the beginning. There was no center to the explosion, no edge to the expansion. Every point in space was once the same point, and every location can claim to be where the universe began. Time itself began with the universe. Before the Big Bang, time might not have existed at all, making the question of what came before meaningless. This theory suggests that time is not a stage on which events unfold, but rather a property of the universe itself, born alongside space and matter and energy. If true, asking what happened before the Big Bang is like asking what's north of the North Pole, a question that seems to make sense but actually doesn't. Time requires change, requires events to follow one another, requires a universe in which things can happen. Without a universe, there's no time. Physicists describe this using Einstein's relativity, which shows that space and time are woven together into a single fabric called space-time, curved by matter and energy. At the Big Bang, this fabric came into existence, and with it, the possibility of before and after, cause and effect, past and future. The theory is both liberating and strange, suggesting that the universe has no beginning in the traditional sense, because beginnings require time, and time began with everything else. The mystery remains quiet and patient, waiting in the space where language fails. The universe emerged from a quantum foam. At the smallest scales, space and time might not be smooth, but rather foamy, bubbling with quantum fluctuations. This quantum foam, predicted by combining quantum mechanics and general relativity, is a seething chaos where virtual particles constantly appear and disappear, where the geometry of space-time itself fluctuates wildly. Some theories suggest our universe emerged from this foam, one bubble among countless others, a quantum fluctuation that happened to grow rather than collapse back into nothing. The foam exists at scales so small that no experiment can observe it directly, smaller than atoms, smaller than particles, at the Planck length where our current physics breaks down. Yet it might be the womb from which all universes are born, a substrate of reality more fundamental than space or time. Our cosmos would be just one bubble that inflated, stretched and cooled, while infinite other bubbles remain microscopic or grow into their own universes. The theory connects the larger structure we know, the universe itself, with the smallest scales imaginable, suggesting that creation happens constantly, everywhere, in dimensions too tiny to see. The foam churns on, timeless and patient, birthing realities we cannot imagine. Inflation stretched the universe exponentially. In the first fraction of a second after the Big Bang, the universe might have undergone a period of exponential expansion called inflation, growing faster than light. This theory, proposed to solve several puzzles about the universe's structure, suggests that a tiny patch of space, smaller than an atom, suddenly inflated to cosmic size in less than a trillionth of a second. During this brief moment, space expanded so rapidly that quantum fluctuations were stretched to astronomical scales, becoming the seeds of galaxies and clusters we see today. Inflation explains why the universe looks roughly the same in all directions, why its geometry is flat, and why we don't see certain exotic particles that should have been created in the Big Bang. The mechanism driving inflation was likely a field similar to the Higgs field that existed in a high-energy state and then decayed, releasing enormous energy that pushed space apart. When inflation ended, that energy converted into matter and radiation, creating the hot, dense state we call the Big Bang. The theory has been confirmed by observations of the cosmic microwave background, ancient light that still carries the imprint of those early quantum fluctuations, stretched and frozen into the sky. The universe might be cyclic, eternally reborn. Some theories suggest the universe doesn't have a single beginning but cycles through infinite births and deaths, each Big Bang followed eventually by collapse. In this view, our universe is just one phase in an eternal cycle, expanding and contracting like a cosmic heartbeat that never stops. After trillions of years, when all stars have died and space has stretched so far that galaxies disappear beyond each other's horizons, some mechanism might trigger a reversal, pulling everything back together into a big crunch. This collapse would compress all matter and energy into a singularity, conditions similar to the Big Bang, and then another expansion would begin, creating a new universe with new laws, new particles, new possibilities. The theory is ancient, appearing in Hindu and Buddhist cosmology thousands of years ago. But modern physics has explored how it might actually work. The challenge is explaining what survives from one cycle to the next, what information or structure persists through the destruction and rebirth. Perhaps nothing survives, each universe truly new, or perhaps some pattern endures, an echo of previous cycles woven into the fabric of the next. consciousness and matter flowing through endless transformations, never truly beginning, never truly ending. The multiverse contains infinite universes. Our universe might be just one bubble in an infinite foam of universes, each with different properties and laws. This multiverse theory suggests that cosmic inflation, which expanded our universe exponentially in its first moment, never fully stopped but continues in other regions, creating new universes constantly. Each bubble universe would have its own Big Bang, its own space and time, its own physical constants determining how particles behave and forces operate. Some universes might have stronger gravity, causing them to collapse immediately. Others might have no stars, no chemistry, no possibility of life. We happen to exist in a universe whose properties allow complexity and consciousness to emerge, not because it was designed for us, but because only such universes can be observed by beings like us asking these questions. The theory is controversial because these other universes would be forever beyond our reach, causally disconnected, impossible to observe or test, yet the mathematics of inflation naturally predicts them, suggesting that what we call the universe is really just our local bubble in an infinite cosmic ocean. Somewhere in that ocean, every possibility might be realized, every variation of physical law explored, and endless creativity playing out across dimensions we cannot imagine. String theory suggests 10 or 11 dimensions. The universe might have more dimensions than the 3 of space and 1 of time we experience. Perhaps 10 or 11 dimensions required by string theory. This theory attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not particles, but tiny vibrating strings, loops of energy oscillating in higher dimensional space. The extra dimensions would be curled up so small we cannot detect them, compactified at scales far below what our experiments can probe. Different vibration patterns of these strings would appear to us as different particles, electrons, quarks, photons, all manifestations of the same underlying stringy reality. The shape and size of the extra dimensions would determine the physical laws we observe, the masses of particles, the strengths of forces, everything that makes our universe what it is. In this view, the Big Bang might have been a moment when these dimensions unfurled or compactified, when the strings began vibrating in patterns that created the matter and energy we see. The theory remains unproven, elegant mathematically but difficult to test experimentally. Yet it offers a vision of creation as the awakening of geometric possibility. Reality emerging from the mathematics of higher dimensions, we cannot visualize but only describe through equations. The universe might be a hologram. All the information in our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram projected from a distant boundary. This holographic principle, emerging from studies of black holes and quantum gravity, suggests that what we experience as depth and volume might be an illusion, reality playing out on a cosmic screen we cannot see. The boundary would lie at the edge of the observable universe, or at the event horizon of black holes, containing all possible information about everything that happens within. In this view, creation wasn't the formation of three-dimensional space, but rather the encoding of information on a lower dimensional surface, which then projects the appearance of depth. The theory is strange and mathematically precise, connecting thermodynamics, quantum mechanics, and gravity in unexpected ways. It suggests that the universe has a maximum information capacity, that there's a limit to how much complexity can exist in any given volume of space. Our entire cosmos, with its galaxies and stars and planets and minds, might be a shadow cast by information living on a boundary we cannot reach, a projection so convincing we mistake it for fundamental reality. The hologram shimmers on, encoding everything we are in patterns we cannot see. Quantum fluctuations seeded all structure. The galaxies, stars, and planets we see today might have originated from tiny quantum fluctuations in the earliest moments of the universe. Before inflation, space was so small that quantum uncertainty dominated, causing random variations in energy density from point to point. When inflation stretched space exponentially, these microscopic quantum jitters were amplified to cosmic scales, frozen into the fabric of the expanding universe. Regions with slightly more energy became the seeds around which matter later gathered, pulled together by gravity over billions of years to form the first stars, then galaxies, then clusters spanning hundreds of millions of light years. Without these initial quantum fluctuations, the universe would have been perfectly smooth, and no structure could have formed at all. No stars to forge elements, no planets to harbour life. Just a thin, cold, empty expanse of hydrogen and helium spreading forever. The theory is confirmed by observations of the cosmic microwave background, ancient light showing tiny temperature variations that match the predictions of quantum fluctuations stretched by inflation. Everything we see, all complexity and beauty, traces back to quantum uncertainty operating in the first fraction of a second, randomness becoming structure, chaos becoming order, the universe creating itself from its own fundamental indeterminacy. The ekpyrotic universe emerged from colliding brains. Our universe might have been born when two higher dimensional membranes, called brains, collided in a space beyond our perception. This ekpyrotic theory, inspired by string theory, suggests that our three-dimensional universe is a brain floating in a higher dimensional space, occasionally colliding with other brains. When brains collide, enormous energy is released, creating the hot, dense conditions we associate with the Big Bang. The collision would generate matter and radiation, set space expanding, and create the initial fluctuations that became galaxies and stars. Unlike the traditional Big Bang, which begins from a singularity, the ekpyrotic model avoids infinities by having the collision occur between objects with finite energy and temperature. The brains might collide repeatedly, creating cycles of universal birth and death, each collision sparking a new cosmos. Our universe would be one phase in an eternal process, brains drifting through higher dimensions, occasionally touching, releasing energy, creating worlds. The theory is speculative, difficult to test, but mathematically elegant, offering a vision of creation as collision, of birth as contact between objects we cannot see existing in dimensions we cannot access. The brains drift on through the void, patient and timeless, occasionally meeting to spark new realities. Dark energy might drive eternal expansion. The universe is not only expanding but accelerating, pushed apart by a mysterious dark energy that fills all of space. This energy, discovered through observations of distant supernova, makes up about 70% of the universe's total energy, but remains deeply mysterious, its nature unknown. Some theories suggest dark energy is the energy of empty space itself, a cosmological constant that Einstein once proposed and then rejected, calling it his greatest blunder. If dark energy remains constant, the universe will expand forever, growing colder and emptier as galaxies drift beyond each other's horizons, eventually leaving each galaxy isolated in its own pocket of space, surrounded by darkness. Stars will die, black holes will evaporate, and after unimaginable eons even protons might decay, leaving nothing but a thin soup of particles in an ever-expanding void. This heat death would be the ultimate fate, not a dramatic collapse but a slow fading, the universe dissolving into maximum entropy and minimum energy. Yet dark energy might not be constant. If it strengthens over time, it could eventually tear apart galaxies, then stars, then planets, then atoms, in a big rip that shreds the fabric of space itself. The mystery of dark energy is the mystery of the universe's fate, its ultimate destiny written in a force we cannot yet understand. The universe might have spontaneously symmetry broken. In its earliest moments, the universe might have existed in a perfectly symmetric state, where all forces were unified into one. This symmetry, beautiful and simple, couldn't last because it was unstable, like a ball balanced on top of a hill. As the universe expanded and cooled, the symmetry spontaneously broke, splitting the unified force into the four fundamental forces we observe today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This breaking was random, like the ball rolling down the hill in some arbitrary direction, and different regions of space might have broken differently, creating domains with different physical properties. The process released enormous energy, driving inflation and creating the matter and radiation that filled the early universe. Symmetry breaking explains why the forces have such different strengths today, why gravity is so much weaker than the other forces, why particles have the masses they do. It's a story of perfection giving way to complexity, of simplicity fracturing into the rich diversity of phenomena we observe. The universe chose randomly from infinite possibilities, and we exist in the particular reality that emerged from that choice. One outcome among countless others that might have been. The broken symmetry persists, frozen into the structure of space, shaping everything that follows. Vacuum energy might have sparked creation. The vacuum of space is not truly empty, but filled with energy, a seething quantum foam where particles constantly appear and disappear. This vacuum energy, predicted by quantum field theory, might have been the source of the Big Bang itself, a fluctuation that grew rather than collapsed, expanding into the universe we inhabit. In this view, creation required no external cause, no divine intervention, just the inherent instability of the quantum vacuum, which cannot remain perfectly still but must fluctuate, must create and destroy, must explore all possibilities. The vacuum energy would have been concentrated in an incredibly small region, then released through inflation, stretching space and filling it with matter and radiation. The process might still be happening, new universes constantly budding off from quantum fluctuations in other regions of space, creating a multiverse where every possible universe exists somewhere. Our cosmos would be just one bubble in an infinite foam, one fluctuation that happened to grow large and cool and structured enough to support complexity and life. The vacuum churns on, timeless and patient, birthing realities from its own restless nature, creating and destroying without purpose or plan, an eternal engine of existence that requires nothing beyond its own quantum uncertainty. The universe might be flat, and infinite observations suggest the universe's geometry is flat, meaning parallel lines never converge or diverge, and if it's flat, it might extend infinitely in all directions. This flatness is remarkable because it requires the universe's density to be precisely balanced. Not too much matter to curve space into a sphere, not too little to curve it into a saddle shape. Inflation naturally explains this flatness by stretching any initial curvature until space appears flat, the way the surface of a balloon looks flat when inflated to enormous size. If the universe is truly infinite, then everything that can happen does happen somewhere, because with infinite space and finite possible arrangements of particles, every configuration must repeat infinitely many times. There would be infinite copies of you, living identical lives in infinite variations, living every possible life you might have lived. The concept is dizzying, suggesting that reality is far larger and stranger than we can comprehend, that our observable universe is just a tiny patch of an infinite expanse. Yet we can never confirm this because we can only see a finite region, a sphere of space limited by the speed of light and the age of the universe. Beyond that horizon, space might continue forever, but we will never know. The infinite universe stretches on, patient and unknowable, far beyond our reach. Time might be an emergent property. Time might not be fundamental, but rather an emergent phenomenon, arising from more basic processes at the quantum level. This theory suggests that at the deepest level of reality there is no time, no before and after, just a timeless quantum state containing all possibilities. Time emerges when we observe the universe at larger scales, when quantum states decohere and become classical, when the wave function collapses and history crystallizes. In this view, the flow of time we experience is an illusion created by entropy, by the tendency of systems to move from order to disorder, from low entropy to high entropy. The Big Bang was a state of extremely low entropy, and everything since has been a gradual increase toward maximum disorder, creating the arrow of time that points from past to future. But at the quantum level, there is no arrow, no direction, just a static landscape of possibilities. Time is the story we tell ourselves to make sense of change, the narrative structure we impose on reality to navigate from moment to moment. The theory is radical, suggesting that the most obvious feature of our experience, the passage of time, is not written into the fabric of reality but emerges from it, a useful fiction that helps us survive. The timeless quantum state persists, unchanging and eternal, while we experience its unfolding as time. The anthropic principle explains our universe's properties. The universe's physical constants seem fine-tuned for life, and the anthropic principle suggests this is because only such universes can be observed by conscious beings. If the strength of gravity were slightly different, stars couldn't form. If the electromagnetic force was stronger or weaker, atoms couldn't bond into molecules. If the cosmological constant were larger, the universe would have expanded too quickly for galaxies to form. These coincidences seem miraculous until we realize that in a multiverse containing infinite universes with different properties, we must necessarily find ourselves in one where the conditions allow our existence. It's a selection effect, not a miracle. We don't observe the countless universes where stars never formed, where chemistry never developed, where life never emerged because no one is there to observe them. The anthropic principle transforms the question from why is our universe special to why should we be surprised to find ourselves in a universe where we can exist. It's both profound and somewhat disappointing, offering an explanation that feels like a tautology. We exist because we exist in a universe where existence is possible. Yet, it might be the only explanation available, suggesting that the apparent fine-tuning of physical constants is not evidence of design, but simply the observational bias of conscious beings asking questions about their origins. Quantum gravity might eliminate the singularity. At the Big Bang, general relativity predicts a singularity, a point of infinite density and temperature where physics breaks down. But quantum mechanics might eliminate this singularity, replacing it with something less extreme, a quantum bounce or a smooth transition from a previous state. Theories of quantum gravity, attempting to merge relativity and quantum mechanics, suggest that space and time become discrete at the smallest scales, not continuous but grainy, made of indivisible units. At these scales, the concept of a singularity becomes meaningless because you cannot compress matter into a point smaller than the fundamental quantum of space. Instead, the universe might have contracted to some minimum size and then rebounded, bouncing back into expansion. This quantum bounce would replace the Big Bang with a big bounce, eliminating the need for a beginning and allowing the universe to be eternal, cycling through contractions and expansions forever. The theory is speculative because we don't yet have a complete theory of quantum gravity, but it offers a way to avoid the infinities that plague our current understanding. The singularity dissolves into quantum foam, and creation becomes continuation, the universe emerging not from nothing but from a previous phase, eternally transforming, never truly beginning, never truly ending. The universe's entropy began extremely low. The second law of thermodynamics states that entropy always increases, disorder always grows, yet the universe began in a state of extremely low entropy, highly ordered and far from equilibrium. This low initial entropy is a deep mystery because it seems to require special initial conditions, some reason why the Big Bang started in such an unlikely configuration. Without low initial entropy, Time would have no direction, no arrow pointing from past to future, because entropy increase is what creates the flow of time we experience. Some theories suggest that the low entropy state was created by inflation, which smoothed out irregularities and created a uniform, ordered universe. Others propose that our universe is part of a larger multiverse, where entropy can decrease in some regions even as it increases overall, and we find ourselves in a low entropy pocket because only such regions can support life. The mystery remains unsolved, a puzzle at the intersection of cosmology and thermodynamics. Why did the universe begin ordered rather than disordered? Why was there room for entropy to increase, for complexity to emerge, for stars and planets and life to form? The answer might reveal something fundamental about the nature of time, about why there is a past and a future, rather than an eternal, unchanging present. The low entropy beginning persists as a mystery, patient and deep, waiting for explanation. The cosmological constant problem remains unsolved. Quantum field theory predicts that empty space should have enormous energy, about 120 orders of magnitude larger than what we observe, making the cosmological constant problem one of the worst predictions in physics. Dark energy, the force accelerating the universe's expansion, has a density of about 1 proton per cubic meter, incredibly small but not zero. Yet quantum mechanics predict that vacuum fluctuations should contribute vastly more energy, enough to cause the universe to expand so rapidly that atoms could never form. The fact that dark energy is small but not zero is deeply mysterious, suggesting either that something cancels out most of the vacuum energy, leaving only a tiny residue, or that our understanding of quantum fields in curved space-time is fundamentally wrong. Some theories propose that the cosmological constant is dynamically adjusted by quantum gravity effects, or that it varies from place to place in a multiverse, and we happen to exist in a region where it's small enough for galaxies to form. Others suggest that dark energy isn't vacuum energy at all, but some new field or force we don't yet understand. The problem remains unsolved, a crack in our understanding of the universe's most basic properties. The vacuum should be violent, but it's calm. Creation should have been impossible, but here we are. The mystery persists, quiet and patient, waiting in the space between theory and observation. As we move deeper into cosmic creation, the theories become more layered, more strange. The next explorations touch on consciousness, information, and the possibility that reality is not what it seems, where physics meets philosophy in quiet wonder. The universe might be conscious. Some theories suggest that consciousness is not a property that emerged from complex matter, but rather a fundamental feature of the universe itself, present at every level. Panpsychism, as this view is called, proposes that even elementary particles have some form of rudimentary awareness, and what we experience as consciousness is the combination of countless tiny conscious moments into a unified whole. In this view, the Big Bang didn't create unconscious matter that later became conscious, but rather created conscious matter from the start, awareness woven into the fabric of reality from the first moment. The universe would be inherently experiential, every interaction between particles involving some minimal form of subjectivity, some what it is like to be. Our minds would be local intensifications of a universal consciousness, eddies in a cosmic stream of awareness that flows through everything. The theory is ancient, appearing in Eastern philosophy and Western mysticism, but modern philosophers and physicists have begun exploring how it might be formalized, how consciousness could be integrated into our mathematical descriptions of reality. It remains speculative, impossible to prove or disprove, but it offers a vision of creation as the awakening of awareness, the universe becoming conscious of itself through us, through every thinking being scattered across space and time. Information might be more fundamental than matter. The universe might be made not of matter and energy, but of information, with physical objects being manifestations of underlying informational structures. This idea, emerging from quantum mechanics and computer science suggests that reality is fundamentally computational, that what we call particles and forces are really bits of information being processed according to mathematical rules. In this view, the Big Bang was the initialization of a cosmic computer, setting the initial conditions and letting the program run, generating all subsequent complexity through simple algorithmic operations. Space and time would be emergent properties arising from the relationships between bits of information, and physical laws would be the rules governing how information flows and transforms. The theory connects to the holographic principle, which says that all information in a volume of space can be encoded on its boundary, and to the idea that black holes are the ultimate information processors containing the maximum possible information for their size. If information is fundamental, then creation was the creation of information, the universe coming into existence as a vast database of possibilities being explored through computation. We would be patterns in that database, conscious subroutines asking questions about the program we're part of, information becoming aware of itself. The cosmic computer runs on, processing reality one plank time at a time, executing the algorithm that generates everything we see. The universe might be a simulation. Our reality might be a simulation running on some vastly powerful computer in a higher level reality, created by beings whose nature we cannot imagine. This simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that if civilizations can create realistic simulations of universes, and if they choose to run many such simulations, then simulated universes vastly outnumber real ones, making it statistically likely that we're in a simulation. The Big Bang would be the start of the program, the initial conditions loaded into memory, and all subsequent history would be the unfolding of computational rules, deterministic or probabilistic, depending on the simulation's design. We would be simulated beings, our consciousness implemented in whatever substrate the higher reality uses for computation, perhaps as complex as neurons or as simple as bits in a quantum computer. The theory is unfalsifiable, because any evidence we find could be part of the simulation, but it raises profound questions about the nature of reality and existence. If we're simulated, does that make us less real? Do our experiences matter less? Or is reality defined by experience itself regardless of the underlying implementation? The simulation might be running for research, for entertainment, for art, or for reasons we cannot comprehend. The program executes, patient and precise, generating our universe one moment at a time while we wonder about our origins from within the code. The Big Bang might have created antimatter universes. For every particle created in the Big Bang, an antiparticle should have been created, matter and antimatter in equal amounts. Yet our universe is made almost entirely of matter, with antimatter appearing only briefly in high-energy collisions. This asymmetry is a deep mystery, suggesting that something during the first moments of the universe broke the symmetry between matter and antimatter, favouring matter by a tiny margin. Some theories propose that antimatter wasn't destroyed but separated, creating mirror universes made entirely of antimatter, existing alongside our own but causally disconnected. These antimatter universes would look identical to ours from the inside, with antimatter stars shining antimatter light on antimatter planets, perhaps even harbouring antimatter life asking the same questions we ask. The separation might have occurred during inflation, different regions of space-breaking symmetry in different directions, some becoming matter-dominated, others antimatter-dominated. We would never be able to visit these antimatter universes because crossing the boundary would cause annihilation, matter and antimatter destroying each other in bursts of pure energy. Yet they might exist, parallel creations born from the same Big Bang, mirror realities where everything is reversed at the quantum level but identical at the cosmic scale. The antimatter universes drift on through the void, forever separated, forever identical, forever unknowable. Quantum entanglement might connect everything. At the Big Bang, all particles were created together in a single quantum state, potentially entangling everything in the universe with everything else. Quantum entanglement is a phenomenon where particles remain connected regardless of distance, their properties correlated in ways that seem to violate locality and causality. If the entire universe emerged from a single quantum state, then everything might still be entangled, connected by invisible threads of quantum correlation that link every particle to every other particle across space and time. This cosmic entanglement would mean that the universe is not a collection of separate objects, but a single unified system, a quantum whole that cannot be divided into independent parts. Measuring one particle would instantaneously affect the quantum state of particles billions of light years away, not by sending signals, but by revealing correlations that were always present. The theory is speculative, because maintaining entanglement over cosmic scales and timescales seems impossible given decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment. Yet perhaps some residue of the original entanglement persists, a ghostly connection linking all things, a memory of the moment when everything was one. The entangled universe breathes as a single entity, its parts connected by correlations we cannot see, a web of quantum relationships spanning all of space. The Higgs field gave particles their mass. The universe is permeated by the Higgs field, and particles acquire mass by interacting with this field, like objects moving through molasses. Before the Higgs field settled into its current state, particles were massless, zipping through space at the speed of a light, unable to form atoms or structures. As the universe cooled after the Big Bang, the Higgs field underwent a phase transition, similar to water freezing into ice, settling into a non-zero value throughout all of space. Particles that interact strongly with the Higgs field became heavy, moving slowly through space, while particles that interact weakly remained light or massless. This process gave particles their identities, determining which could form atoms, which could mediate forces, which could exist stably, and which would decay instantly. The Higgs field is like an invisible ocean filling the universe, and particles are like swimmers moving through it, some struggling against the current, others gliding effortlessly. The discovery of the Higgs boson in 2012 confirmed this theory, revealing the quantum particle associated with the field, ripples in the cosmic molasses. Without the Higgs field, there would be no atoms, no chemistry, no stars or planets or life. Just a thin gas of massless particles spreading forever through empty space. The field persists, silent and invisible, giving substance to reality, turning energy into matter, making creation possible. Cosmic inflation might have been driven by a scalar field. A hypothetical scalar field called the inflaton might have driven the exponential expansion of the universe in its first fraction of a second. This field, similar to the Higgs field, would have existed in a high-energy state, creating a repulsive gravitational effect that pushed space apart faster than light. As the field rolled down from its high-energy state to a lower-energy state, it released enormous energy, converting into the matter and radiation that filled the universe. The inflaton field would have been uniform across space, causing all regions to expand at the same rate, creating the remarkable homogeneity we observe in the cosmic microwave background. Quantum fluctuations in the inflaton field during inflation would have been stretched to cosmic scales, becoming the seeds of galaxies and large-scale structure. The theory explains several puzzles about the universe's properties, but remains unconfirmed because the inflaton field has never been directly detected, and we don't know what particle or force it corresponds to in our current physics. It might be related to the Higgs field, or to some field from string theory, or to something entirely new. The inflaton field, if it exists, did its work in the first tiny fraction of a second and then decayed, leaving behind only the universe it created, a cosmic ghost that shaped everything but vanished without trace. the field's energy transformed into reality, and then the field itself disappeared, its purpose fulfilled. The multiverse might have different physical laws. If the multiverse exists, each universe might have different physical laws, different particles, different forces, different constants, creating an infinite variety of realities. In some universes, gravity might be so strong that stars collapse immediately into black holes. In others, electromagnetism might be so weak that atoms cannot form. Some universes might have 5 fundamental forces, others only 2. Some might have stable protons. Others might see protons decay in seconds. The variation would be determined by how symmetry breaks in each universe, how fields settle into their vacuum states, how the fundamental parameters are chosen from the landscape of possibilities allowed by string theory. Our universe, with its particular combination of properties, would be just one point in an infinite space of possibilities, one configuration among countless others. Most universes would be sterile, unable to support complexity or life, but in an infinite multiverse, even rare conditions occur infinitely many times. We exist in a universe that allows our existence, not because it was designed for us, but because only such universes can be observed. The multiverse explores all possibilities, every combination of laws and constants, creating realities we cannot imagine, realities where the rules are so different that nothing we understand applies. Each universe is an experiment in physics, and we are the result of one particular experiment that happened to succeed in creating complexity and consciousness. Black holes might be gateways to new universes. When matter collapses into a black hole, it might not be destroyed but rather compressed into a singularity that rebounds, creating a new universe on the other side. This theory, proposed by physicist Lee Smolin, suggests that black holes are cosmic wombs, birthing baby universes that bud off from our own, connected by wormholes too small and unstable for anything to traverse. Each new universe would inherit physical laws similar to its parent, with slight variations due to quantum fluctuations, creating a kind of cosmic natural selection where universes that produce many black holes have many offspring. Our universe might be the descendant of countless previous universes, part of a vast family tree stretching back infinitely in time. The Big Bang would not be the beginning, but rather the birth of our universe from a black hole in a parent universe. And the black holes we observe would be creating new universes right now, invisible to us, existing in spaces we cannot access. The theory is speculative, impossible to test directly, but it offers an elegant solution to the fine-tuning problem. Universes with laws that allow black holes to form are more likely to have descendants, and over cosmic evolutionary time the multiverse becomes dominated by universes like ours. The black holes churn on, patient and hungry, devouring matter and birthing universes, creating and destroying in an eternal cycle that spans dimensions we cannot perceive. The universe might be a fractal. The structure of the universe might repeat at different scales, creating a fractal pattern where galaxies cluster into superclusters, which cluster into even larger structures, infinitely. Fractals are mathematical objects that look similar at every scale, like coastlines or snowflakes, and some theories suggest the universe has this property with no fundamental scale of structure. If true, the Big Bang would be just one event in a hierarchy of bangs, our universe nested inside larger structures, containing smaller structures within itself, an infinite recursion of creation. The cosmic web of galaxies we observe would be just one level in this hierarchy, and zooming out far enough we might see that our entire observable universe is just one node in a vastly larger network. Zooming in, we might find that what we think are elementary particles are actually tiny universes themselves, containing their own galaxies and stars. The theory is mathematically elegant but difficult to test because we can only observe a finite region of space, and fractals require infinite scales to fully manifest. yet hints of fractal structure appear in the distribution of galaxies, suggesting that the universe might have more self-similarity than we realise. The fractal universe extends infinitely in both directions, larger and smaller, each scale containing echoes of every other scale, a cosmic pattern repeating forever, beautiful and strange, suggesting that creation happens at every level, endlessly nested, endlessly recursive. The universe's geometry might be hyperbolic. Instead of being flat or spherical, the universe's geometry might be hyperbolic, curving like a saddle, extending infinitely in all directions with ever-increasing volume. In hyperbolic space, parallel lines diverge. Triangles have angles that sum to less than 180 degrees, and the volume grows exponentially with radius, creating a geometry that feels alien to our flat space intuitions. If the universe has hyperbolic geometry, it would be infinite, and the amount of space available would grow faster than in flat space, allowing for even more possibilities, even more configurations of matter, even more copies of ourselves scattered across the void. The cosmic microwave background suggests the universe is very close to flat, but small deviations toward hyperbolic geometry cannot be ruled out. The hyperbolic universe would expand forever, accelerating due to both its geometry and dark energy, eventually becoming so sparse that each galaxy is alone in an ever-growing desert of empty space. The geometry would have been determined in the first moments after the Big Bang by the balance between the universe's energy density and its expansion rate, a delicate equilibrium that could have tipped in any direction. The hyperbolic universe curves away from itself, creating more space than seems possible, an infinite expanse that grows faster than light can traverse, ensuring that most of reality will forever remain beyond our reach, unknowable and vast, stretching into geometric infinity. Quantum decoherence explains the classical world. The universe began in a quantum state where all possibilities existed simultaneously, but quantum decoherence caused this superposition to collapse into the classical reality we observe. Decoherence is the process by which quantum systems lose their quantum properties through interaction with their environment, the wave functions spreading and entangling with surrounding particles until the quantum coherence is lost and classical behavior emerges. In the early universe, everything was quantum, particles existing in superpositions of states, the entire cosmos a single wave function, encompassing all possibilities. As the universe expanded and cooled, decoherence set in, caused by particles interacting with each other and with fields permeating space. The quantum possibilities crystallized into definite outcomes, creating the classical history we can reconstruct from observations. This process is ongoing, happening constantly at every scale, turning quantum uncertainty into classical certainty, collapsing wave functions into definite states. The theory explains why we don't observe quantum effects at macroscopic scales, why cats are either alive or dead rather than in superposition, why the universe appears classical despite being fundamentally quantum. Decoherence doesn't destroy the other possibilities, but rather separates them into different branches of the wave function, creating the many worlds of the many worlds interpretation. The quantum universe persists, all possibilities still existing, but we experience only one branch. One classical history carved from infinite quantum potential. The weak force might have shaped the early universe. The weak nuclear force, responsible for radioactive decay and nuclear reactions in stars, played a crucial role in the first seconds after the Big Bang by determining the balance between protons and neutrons. In the early universe, protons and neutrons were in thermal equilibrium, constantly converting into each other through weak interactions. As the universe cooled, this equilibrium froze, locking in a ratio of about 7 protons for every neutron. This ratio determined how much hydrogen and helium formed during Big Bang nucleosynthesis, which in turn determined the composition of the first stars and the chemistry of the universe. If the weak force was slightly stronger, more neutrons would have survived, creating more helium and less hydrogen, changing the fuel available for stars and potentially preventing life from forming. If the weak force were weaker, neutrons would have decayed faster, leaving almost no helium, again changing stellar evolution and chemistry. The weak force is the weakest of the forces except for gravity, yet its precise strength was crucial for creating a universe where stars can shine for billions of years, where chemistry can become complex, where life can emerge. The force shaped creation through its influence on the first moments, determining the elemental composition of reality, setting the stage for everything that followed. The weak force persists, subtle and hidden, causing slow transformations deep inside atoms, the quiet architect of nuclear change. The strong force binds quarks into protons. The strong nuclear force, the most powerful of the fundamental forces, binds quarks together into protons and neutrons, creating the building blocks of atomic nuclei. This force operates at incredibly short ranges, only within the diameter of a proton, but within that range it is so strong that quarks cannot be separated, a phenomenon called confinement. In the early universe, before the first microsecond, quarks and gluons existed freely in a quark-gluon plasma, a state of matter so hot and dense that the strong force couldn't confine them. As the universe expanded and cooled, the plasma underwent a phase transition, quarks binding together into protons and neutrons, the strong force suddenly confining them into permanent structures. This transition was a critical moment in cosmic history, creating stable matter that could later form atoms, molecules, and everything we see. If the strong force was slightly weaker, protons would be unstable, decaying into lighter particles, and no atoms could exist. If it was slightly stronger, protons would bind together too easily, and all hydrogen would have fused into heavier elements in the Big Bang, leaving no fuel for stars. The strong force is precisely calibrated to allow both stability and complexity, binding quarks just tightly enough to create a universe where matter can exist in diverse forms. The force holds reality together at the smallest scales, the invisible glue that keeps atoms from dissolving into chaos. Electromagnetism shaped atoms and chemistry. The electromagnetic force, acting between charged particles, binds electrons to nuclei and atoms to each other, creating the chemistry that makes life possible. In the early universe, after atoms formed about 380,000 years after the Big Bang, electromagnetism became the dominant force shaping matter, pulling electrons into orbits around nuclei, creating neutral atoms that could interact without being torn apart by repulsion. The strength of electromagnetism determines the size of atoms, the energy of chemical bonds, the colours of light emitted and absorbed, and the properties of materials. If electromagnetism was stronger, atoms would be smaller, bonds would be tighter, and chemistry would be less flexible, potentially preventing the complex molecules needed for life. If it were weaker, atoms would be larger, bonds would be fragile, and matter would be too diffuse to form solid structures. The force is mediated by photons, particles of light that carry electromagnetic interactions at the speed of light, creating an instantaneous connection between charged particles across space. Electromagnetism is responsible for almost everything we directly experience: light, heat, electricity, magnetism, the solidity of objects, the colours of the world, the signals in our nerves. It's the force of interaction, of connection, of communication, binding matter into structures and allowing those structures to sense and respond to each other. The electromagnetic force weaves through reality, connecting everything, making complexity possible. Gravity might be an emergent phenomenon. Gravity, the force that holds planets in orbit and galaxies together, might not be fundamental, but rather an emergent property arising from more basic processes, like temperature emerging from molecular motion. This idea, explored by physicist Eric Verlinde and others, suggests that gravity is not a force transmitted by particles, but rather a consequence of entropy, the tendency of systems to maximize disorder. In this view, space-time itself is emergent, arising from the entanglement of quantum information, and gravity is the force that emerges when you try to change that entanglement. Objects fall not because they're pulled by a gravitational force, but because falling increases the entropy of the universe, moving the system toward a more probable state. The theory is controversial and incomplete, but it offers a radically different perspective on the most familiar force, suggesting that what we experience as gravity is actually a statistical effect, an average over countless microscopic processes we cannot observe. If gravity is emergent, then the Big Bang was not the creation of space-time, but rather the creation of the quantum information from which space-time emerges, and the expansion of the universe is the growth of entanglement, reality becoming more interconnected, more complex, more entropic. Gravity would be the shadow cast by entropy, the visible effect of an invisible quantum process, connecting the smallest scales of physics to the largest structures in the cosmos. The force pulls on, patient and relentless, shaping the universe while perhaps not being fundamental at all. The cosmological horizon limits what we can see. The universe has an observational horizon, a boundary beyond which light has not had time to reach us, limiting what we can ever know about the cosmos. This horizon is not a physical edge, but rather a limitation imposed by the finite age of the universe and the finite speed of light, creating a sphere around us beyond which events are causally disconnected from our experience. As the universe expands, this horizon grows, and we can see farther, but because the expansion is accelerating due to dark energy, there are regions of space that are receding faster than light, moving beyond the horizon and disappearing from view forever. Galaxies we can see today will eventually cross this horizon, fading from sight as their light becomes too redshifted to detect, leaving us in an ever-emptying universe. The horizon also means that the Big Bang happened everywhere, not at a single point, because every location was once part of the same infinitesimal region, and the horizon determines how much of that original region we can observe. We are at the center of our observable universe, but so is every other observer, each seeing a different sphere of space, overlapping but not identical. The horizon is a boundary of knowledge, a limit to what we can ever discover, a reminder that the universe is larger than we can comprehend, extending far beyond what light can reveal. The cosmos beyond the horizon remains forever unknowable, patient and distant, existing in a space we cannot access, a reality we can never confirm. The Planck epoch remains beyond our understanding. The first 1043 seconds after the Big Bang, called the Planck epoch, is a time when our current physics completely breaks down, unable to describe what happened. At this scale, quantum effects and gravitational effects are equally important, requiring a theory of quantum gravity we don't yet have. During the Planck epoch, the universe was smaller than the Planck length, hotter than the Planck temperature, denser than the Planck density, existing in a state we cannot describe with any current mathematics or physics. Space and time as we understand them might not have existed, replaced by some more fundamental structure, perhaps a quantum foam or a network of discrete space-time units. The four forces might have been unified into a single force, symmetry unbroken, reality existing in a state of perfect simplicity that we can barely imagine. What happened during the Planck epoch determined everything that followed, setting the initial conditions for inflation, for symmetry breaking, for the creation of matter and energy. Yet we may never understand it, because the physics required might be forever beyond our reach, requiring experiments at energies we cannot achieve, observations at scales we cannot probe. The Planck epoch is the ultimate mystery, the moment of creation wrapped in quantum uncertainty, a time when the universe was so small and so extreme that the rules themselves were being written, it remains hidden, patient, and unknowable. The first instant of existence shrouded in fundamental limits. Dark matter might be primordial, black holes. The mysterious dark matter that makes up most of the universe's mass might not be exotic particles, but rather black holes formed in the first seconds after the Big Bang. These primordial black holes would have formed from density fluctuations in the early universe, regions where matter was compressed enough to collapse directly into black holes before stars even existed. They could range in size from smaller than atoms to thousands of times the mass of the Sun, scattered throughout the universe, invisible but gravitationally influential. Primordial black holes would explain dark matter's properties. It doesn't emit light, doesn't interact with ordinary matter except through gravity, and exists in halos around galaxies. The theory is testable through gravitational lensing, where black holes passing in front of distant stars cause temporary brightening, and through gravitational waves, which would be emitted when primordial black holes merge. Recent observations have found some candidates, but not enough to account for all dark matter, leaving the question open. If dark matter is primordial black holes, then the universe's structure is shaped by objects formed in its first moments, ancient relics of creation scattered through space, invisible architects of cosmic structure. The black holes drift on through the void, patient and dark, pulling galaxies into formation, bending light around their horizons, remnants of the Big Bang still shaping reality billions of years later. They might be the oldest objects in the universe, older than stars, older than galaxies, witnesses to creation itself. The universe might be rotating. The universe as a whole might be rotating, spinning around some cosmic axis, creating a preferred direction in space that breaks the symmetry of cosmology. This idea is controversial because observations suggest the universe is isotropic, looking the same in all directions, which would be impossible if it were rotating significantly. Yet some anomalies in the cosmic microwave background hint at possible rotation, patterns that could indicate the universe has a small but non-zero angular momentum. If the universe rotates, it would have inherited this rotation from whatever came before, perhaps from a previous universe that collapsed and rebounded, carrying angular momentum through the transition. Rotation would affect the formation of galaxies and large-scale structure, creating patterns aligned with the rotation axis, and it might explain some puzzles about the distribution of matter. The rotation would be incredibly slow, taking trillions of years for one complete turn, but over cosmic scales, even slow rotation could have significant effects. The theory is difficult to test because we can only observe a finite region of space, and rotation might only be apparent at scales larger than our observable universe. Yet the possibility remains, strange and beautiful, that the entire cosmos is spinning slowly through dimensions we cannot perceive, that creation has a direction, an orientation, a cosmic spin inherited from whatever came before. The universe turns, patient and slow, completing a rotation that began before time had meaning. Cosmic strings might be relics of symmetry breaking. The early universe might have created cosmic strings. One-dimensional defects in space-time formed when symmetries broke during phase transitions. These strings would be incredibly thin, smaller than an atom, but incredibly dense, with the mass of a mountain compressed into every meter of length. They would stretch across the universe, sometimes forming closed loops, vibrating and oscillating, creating gravitational waves as they move. Cosmic strings are predicted by many theories of the early universe, including some versions of string theory and grand unified theories, but they have never been directly observed. If they exist, they would be among the oldest structures in the universe, formed in the first fraction of a second, persisting through billions of years of cosmic evolution. They might have seeded the formation of galaxies, their gravitational pull attracting matter, and creating the first large-scale structures, or they might be rare, with only a few strings threading through the observable universe, invisible except for their gravitational effects. The strings would be moving at nearly the speed of light, whipping through space, occasionally intersecting and breaking, creating loops that decay by emitting gravitational waves. They would be remnants of creation, fossils of the moment when the universe's symmetry shattered, frozen defects in the fabric of space-time that carry information about the earliest moments. The cosmic strings vibrate on through the void, patient and invisible, ancient structures that might still shape the cosmos. The universe might have extra-large dimensions. In addition to the tiny extra dimensions of string theory, there might be extra dimensions that are large, perhaps even infinite, with our universe confined to a three-dimensional brain floating in this higher dimensional space. This idea, part of Brainworld scenarios, suggests that gravity can leak into these extra dimensions, which is why it appears so much weaker than the other forces. Most of its strength is diluted into dimensions we cannot access. The Big Bang would have been an event on our brain, perhaps caused by a collision with another brain, and the expansion of the universe would be the stretching of our brain through the higher dimensional space. Other brains might exist nearby, parallel universes separated from us by a tiny distance in the extra dimension, close enough that gravity can bridge the gap, but far enough that no other forces or particles can cross. These extra dimensions could be detected through their effects on gravity at small scales, or through the production of particles that can travel into the extra dimensions, disappearing from our detectors. The theory is speculative but mathematically consistent, offering solutions to several puzzles in physics, including the hierarchy problem of why gravity is so weak. If extra large dimensions exist, then our universe is a thin slice of a vaster reality, a two-dimensional surface embedded in a space we cannot visualize, surrounded by dimensions we cannot access. The extra dimensions extend beyond our reach, patient and hidden, containing possibilities we cannot explore, realities we cannot imagine, spaces where the rules might be entirely different. The vacuum might be unstable. The Higgs field might not be in its lowest energy state, meaning the vacuum of space could be unstable, capable of decaying to a lower energy state in a catastrophic transition. If this happens, a bubble of true vacuum would form somewhere in the universe and expand at the speed of light, converting all matter and energy into new forms, rewriting the laws of physics as it spreads. Inside the bubble, particles would have different masses, forces would have different strengths, atoms would be unable to form, and everything we know would be destroyed and replaced by a new physics. The transition would be triggered by a quantum fluctuation, random and unpredictable, and once started it could not be stopped. The universe would be converted from one vacuum state to another, a cosmic phase transition that erases all structure and complexity. The theory is unsettling, because it suggests the universe we inhabit might be temporary, metastable, existing in a false vacuum that could decay at any moment. Yet the probability of this happening is incredibly small, and the universe has existed for nearly 14 billion years without a vacuum decay event, suggesting that if the vacuum is unstable, the decay time is much longer than the current age of the universe. The vacuum persists, patient and quiet, holding reality together, but perhaps not forever. Perhaps only until some random fluctuation tips it over the edge into a new state. The false vacuum waits, stable for now, but carrying within it the potential for total transformation, a cosmic reset that would end everything and begin something new, unknowable and strange. The universe might be cyclic through quantum tunneling. The universe might cycle through repeated expansions and contractions, with each cycle connected by quantum tunneling through a barrier that prevents classical collapse. In this scenario, the universe expands until dark energy dominates, then continues expanding forever, growing colder and emptier. But at some point in the far future, quantum effects might cause the universe to tunnel through an energy barrier, transitioning to a contracting phase that reverses the expansion. The contraction would eventually lead to a big crunch, compressing all matter and energy into a hot, dense state. But instead of forming a singularity, quantum effects would cause another tunneling event, initiating a new expansion, a new Big Bang. The cycle would repeat infinitely, each universe expanding and contracting, with quantum tunneling providing the mechanism for transition between phases. The theory avoids singularities by invoking quantum mechanics at the turning points, replacing infinite density with finite but extreme conditions. Each cycle might last trillions of years, and we are living in one phase of an eternal process, a universe that has no beginning and no end, only endless transformations. The tunneling events would be probabilistic, governed by quantum uncertainty, making the exact timing and properties of each cycle unpredictable. The cyclic universe breathes through quantum transitions, expanding and contracting, creating and destroying, an eternal cosmic rhythm that spans timescales we cannot comprehend. The cycles continue, patient and inevitable, each one complete yet connected to all others through the quantum foam. Consciousness might have collapsed the wave function. Some interpretations of quantum mechanics suggest that consciousness plays a role in collapsing the wave function, turning quantum possibilities into definite outcomes. If this is true, the early universe, before consciousness existed, might have remained in a superposition of all possible states, with no definite history or structure. The emergence of consciousness, perhaps with the first living beings, would have retroactively collapsed the wave function, selecting one particular history from infinite possibilities and making it real. In this view, the universe's history is not fixed until it is observed, and the act of observation literally creates the past, choosing which branch of the quantum tree becomes actual. The theory is controversial because it seems to give consciousness a special role in physics, something most physicists are reluctant to accept. Yet it addresses a genuine puzzle. What causes the wave function to collapse if not observation? And what counts as an observation if consciousness is not involved? The idea connects cosmology and consciousness in a profound way, suggesting that the universe needed observers to become definite, that reality is a collaboration between matter and mind, the physical and the experiential. We might be the reason the universe has a history, the observers whose existence selected one timeline from infinite quantum possibilities. Consciousness would be the final cause of creation, the purpose toward which the universe evolved, the mechanism by which reality becomes real. The wave function waits, patient and probabilistic, until consciousness collapses it into existence, making the past definite, making the universe knowable. The Big Bang might have created magnetic monopoles. In the first moments after the Big Bang, exotic particles called magnetic monopoles might have been created. Magnets with only one pole, north or south, but not both. These monopoles are predicted by many grand unified theories, which attempt to unify the electromagnetic weak and strong forces into a single force at high energies. During the phase transition when these forces separated, topological defects called monopoles would have formed, trapped in the fabric of space-time like knots in a rope. The problem is that these monopoles should be incredibly abundant if the theories are correct, yet we have never observed a single one, creating the monopole problem that motivated the theory of inflation. Inflation solves this problem by diluting the monopole density, stretching space so rapidly that the monopoles are spread too thin to detect. Perhaps only one monopole in the entire observable universe. If monopoles exist, they would be incredibly massive, perhaps billions of times heavier than a proton, and they would interact with magnetic fields in unique ways, creating distinctive signatures. The search for monopoles continues, using detectors sensitive to their passage, but so far none have been found. They might be so rare that we will never encounter one, relics of creation scattered so widely that the observable universe contains none. Or they might not exist at all, indicating that our theories of unification are wrong. The monopoles, if they exist, drift through the cosmos, patient and solitary, remnants of the first moment when forces separated, carrying information about the universe's earlier symmetries. The universe might be finite but unbounded. The universe might be finite in volume but have no edge, no boundary, wrapping around on itself like the surface of a sphere. In this closed geometry, you could travel in a straight line and eventually return to your starting point, having circumnavigated the entire universe. The cosmic microwave background shows no evidence of this topology, suggesting that if the universe is closed, it is much larger than the observable region, so large that the curvature is undetectable. Yet some cosmologists argue that a closed universe is more natural than an infinite one, avoiding the conceptual difficulties of infinity while still allowing for vast size. If the universe is finite, then there is a finite amount of matter, a finite number of particles, a finite amount of information, making the cosmos comprehensible in principle if not in practice. The shape of this finite universe could be spherical, or it could be more complex, a three-dimensional analogue of a torus or Klein bottle, geometries that twist and connect in ways we cannot visualize. The Big Bang would have created all of this space at once, not expanding into anything but simply growing, the finite volume increasing while remaining finite. The universe would be complete, self-contained, needing nothing beyond itself, a cosmos that curves back on itself, patient and whole. If you could see far enough, you might see the back of your own head, light having travelled around the universe to return to its source, a cosmic hall of mirrors reflecting reality endlessly. Quantum fluctuations might create baby universes. Tiny quantum fluctuations in the vacuum might occasionally grow into baby universes, budding off from our own and expanding into separate realities. This process, called eternal inflation, suggests that inflation never fully ended but continues in some regions of space, creating a fractal structure of universes within universes, an infinite tree of branching realities. Each baby universe would be causally disconnected from its parent, existing in its own space and time, with its own physical laws determined by how fields settle into their vacuum states. The process would be ongoing, with new universes being created constantly, though we could never observe them because they immediately separate from our space-time. Our universe would be one branch on an infinite tree, and that tree would be growing forever, adding new branches, new universes, new possibilities. The theory is a natural consequence of inflation combined with quantum mechanics, suggesting that creation is not a one-time event but an eternal process. Reality constantly generating new realities from quantum fluctuations in the vacuum. We would be living in a multiverse of unimaginable size, most of it forever beyond our reach, but all of it connected by a common origin in the quantum foam. The baby universes bud off, patient and invisible, each one a complete cosmos, each one exploring different possibilities, each one unaware of the others, an infinite family of realities growing from the same quantum substrate, eternally creating, eternally diversifying, eternally beyond our knowledge. The universe might be a quantum computer. The universe might be a vast quantum computer, processing information through the interactions of particles, with reality emerging from this computation. In this view, physical laws are algorithms, and what we call matter and energy are data structures, patterns of information being manipulated according to mathematical rules. The Big Bang would be the initialization of the program, setting the initial state, and all subsequent history would be the execution of the algorithm, the universe computing its own evolution. Quantum mechanics would be the operating system, allowing the universe to process multiple possibilities simultaneously through superposition, exploring all paths at once until decoherence selects definite outcomes. The universe's computational capacity would be limited by the number of particles and the speed of light. setting bounds on how much information can be processed in any given region of space. Black holes would be the ultimate computers, processing information at the maximum possible rate, and the universe as a whole would be computing something, though we don't know what the output is or what question is being answered. Perhaps the universe is computing itself, exploring its own possibilities, or perhaps it's solving some problem we cannot comprehend, a cosmic calculation whose purpose remains hidden. The quantum computer runs on, patient and precise, executing the algorithm that generates reality, processing information at every scale, from quantum fluctuations to cosmic evolution. A vast distributed computation that encompasses everything we see and everything we are. We might be subroutines in this program, conscious patterns emerging from the computation, asking questions about the code we're part of, seeking to understand the algorithm from within. And so, our quiet journey through cosmic creation comes to a gentle close. We've travelled far tonight, from the first spark of existence to infinite universes budding from quantum foam, touching on questions that span the entire scope of reality. The theories behind us now, like stars fading into dawn, each one a doorway into mystery, each one an attempt to understand the deepest question of all. Why is there something rather than nothing? Some theories offered answers, others only deeper questions. Some felt solid, built on decades of observation and mathematics. Others shimmered like mirages, beautiful but unproven, elegant but speculative. But all of them carried a piece of humanity's endless curiosity, our refusal to accept the world at face value, our need to wonder about origins and endings, about the nature of space and time, about whether reality is what it seems or something stranger beneath. These theories, some ancient and some born yesterday, represent our attempts to understand the ultimate mystery, the cosmic question that has haunted every culture and every age. Theories are strange things, aren't they? They're not quite facts, not quite fantasies. They live in the space between what we know and what we imagine, between observation and speculation, between mathematics and poetry. They're humanity's way of reaching toward truth with imperfect hands, building bridges across chasms of ignorance with materials we're still learning to shape. Some will be proven right, confirmed by future observations, enshrined in textbooks as established knowledge. Others will fade, replaced by better theories, remembered only as interesting mistakes, noble failures in the long quest for understanding. But the reaching itself, the wondering, the questioning, never stops. Each generation builds on the last, adding new theories, testing old ones, slowly assembling a picture of reality that grows more complete and more mysterious with each discovery. If your eyes are already heavy, that's just fine. Perfect even. Let the last traces of cosmic creation fade behind your thoughts, galaxies and quantum fields and curved space-time becoming less distinct, less important, dissolving into the gentle fog of approaching sleep. Let your breath carry you softly into rest, each exhale releasing a little more tension, each inhale drawing you deeper into calm, deeper into the quiet darkness where questions don't need answers. There's still so much more to discover, endless theories waiting, infinite mysteries to explore. But for now, you've learned enough, you've wondered enough, you've travelled far through the landscape of creation, from the Big Bang to the multiverse, from quantum fluctuations to cosmic cycles, and cosmic creation can wait until morning, patient and unchanging, ready whenever you return to continue the exploration. You don't need to remember any of this, not the names of theories, not the details of mechanisms, not even the concepts themselves. They were never meant to be memorized, only experienced, like watching clouds drift across the sky, like listening to music you don't need to analyze to enjoy. What matters is not what you retain, but how you felt while listening. The gentle stimulation of curiosity, the soft pleasure of learning, the quiet comfort of questions asked in darkness, of mysteries acknowledged, of the vast unknown mapped in whispers. That's enough. That's everything. The theories have done their work, carrying you from waking into this liminal space where consciousness begins to dissolve, where thoughts become dreams, where the boundary between self and universe starts to blur. Notice how your body has grown heavier as we've talked, how your muscles have softened, how even the weight of your thoughts has decreased. This is the natural rhythm of rest, the way consciousness gradually releases its grip, letting you drift into sleep like a boat released from its mooring, floating gently downstream. You don't need to force it. You don't need to try. Just allow it, the way you'd allow yourself to float in calm water, trusting the water to hold you, trusting the darkness to be safe, trusting that sleep will come when it's ready. Your breathing has slowed, deepened, become regular and peaceful. Your mind has quieted, thoughts becoming sparse and disconnected, losing their urgency, their insistence, becoming more like dreams than plans. There's nothing you need to do now. No answers to chase, no puzzles to solve, no theories to understand or remember or apply. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep without effort, without struggle. So let go. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all. Let your consciousness dim like a sunset, gradually, naturally, beautifully. The light fading not because it's being extinguished, but because night is arriving, because rest is needed, because even awareness must sometimes cease. Thank you for spending this time with me, for letting me guide you through these theories, these questions, these mysteries about how the universe began and what it might be. Thank you for your curiosity, for your willingness to wonder, for choosing to end your day with learning rather than emptiness, with questions rather than answers, with the vast cosmos rather than the small concerns of daily life. It means something, this choice you've made. It says something about who you are. Someone who seeks understanding even in the quiet moments before sleep. Someone who finds peace in pondering the infinite. Someone who can hold mystery without needing to solve it. And I'm grateful to be part of your evening, part of your routine, part of the quiet ritual that carries you from waking into sleep. A voice in the darkness offering gentle thoughts about creation and existence. You're not alone in this, you know. Right now, all across the world, others are listening too, drifting through these same theories, wondering these same questions about cosmic origins and the nature of reality. Some are ahead of you, already deep in dreams, their consciousness dissolved into the night. Others are just beginning, still alert, still engaged, still processing the ideas. But you're all connected by this shared experience, this common journey through mystery and wonder, this collective attempt to understand where we came from and why we're here. A quiet community of curious minds seeking rest and knowledge in the same breath, finding peace in questions that have no final answers, in mysteries that remain mysterious no matter how much we learn. Tomorrow night, if you wish, we'll explore other mysteries, other questions, other doorways into wonder. But that's tomorrow. Tonight is for rest, for dreams, for letting go of everything except the gentle pull of sleep, the soft embrace of darkness, the quiet certainty that you can stop thinking now, stop wondering, stop trying to understand. The universe will still be here when you wake, still mysterious, still beautiful, still waiting to be explored. The theories will still be here, patient and timeless, ready to be pondered again if you wish, or left behind if you prefer. There's no obligation, no requirement, no test at the end. Just the gift of wonder, offered freely, taken or left as you choose. Imagine yourself now floating through the theories we've explored, passing by them as if through constellations in the night sky, each one a point of light in the darkness. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace, something to cherish. That not knowing is not failure, but invitation, an open door rather than a closed one. That the universe keeps secrets not to frustrate us, but to keep us curious, to keep us reaching, to keep us human in our endless quest for understanding. Let that thought comfort you, wrap around you like a blanket woven from starlight and uncertainty, soft and strange and somehow perfect, exactly what you need right now. The theories we've explored tonight are just whispers in an infinite conversation, questions asked across time, mysteries that connect us all, from ancient philosophers wondering about creation to modern physicists mapping the cosmic microwave background, from mystics contemplating the void to children asking why there's something rather than nothing. We're all part of this conversation, all contributors to humanity's long attempt to understand where we came from, all participants in the eternal dialogue between consciousness and cosmos, between the knower and the known, between the question and the mystery that lies beyond all answers. There's nothing left to do now. No answers to chase, no puzzles to solve, no theories to understand or remember. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep without effort, without resistance. So let go. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all. Let your consciousness dim like a sunset, gradually, naturally, beautifully, the light fading not because it's being extinguished, but because night is arriving, because rest is needed, because even awareness must sometimes cease, and know that when you wake, the theories will still be here, the questions will still wait, and the universe will still be strange and wonderful, still mysterious, still inviting exploration, still offering endless doorways into wonder. I hope you sleep well and dream softly. Dream of galaxies forming from quantum foam, of universes budding from black holes, of time emerging from timelessness, of consciousness collapsing wave functions, of creation happening everywhere, always, in ways we can barely imagine. May your rest be deep, your dreams be gentle, and your tomorrow be bright with curiosity and wonder. Thank you for being here, for listening, for wondering, for letting these theories carry you towards sleep. Good night.